perfectly stable IPI system for input out stable if the H infinity norm is bounded, no? Which of course just means I don't have anything, I don't have any poles on the imaginary axis or on the otherwise fine. Something that is also very useful, we also learned in the math course, that's what is called Young's inequality. So here you can essentially see that if you take the convolution of two signals, you measure it in the R norm, where R is just any number greater or equal to 1. And this is smaller or equal than the P norm of G times the Q norm of U, where P and Q have the standard relationship that 1 plus P plus 1 plus Q has to be equal to 1 plus 1 divided by R. So in particular, if you use, let's say, P equals to infinity, and Q equals to 1, then what do you do for your R? Yes. And that's how you get, for instance, these bounded input, bounded output stability kind of thing. But also. And so this is a general inequality that we don't teach in linear systems. And this is essentially, if you don't want to go through all the exponentials and all of this, you could get it directly from Young's inequality. Now you could see that if I choose, I mean, you can also choose here I equals to infinity, and so you could do it the other way around as well. But I didn't do it here. Why didn't I do it under? Did I want to do it the other way around? No, I didn't want to do that. Okay, so there are two comments, really. One is, I can choose here infinity, and I can obviously choose here infinity, and then I would get here 1, right? And this is something you have seen in the linear systems course, saying that input-output of Bible stability is equivalent to saying that the one norm of the impulse response is smaller than infinity. I think that's something that you have learned. I hope it is. Did you learn it? Mechanical engineers learned it. Did you learn it? Okay, that's crazy. So what is Bible stability? Bible stability means bounded input and to get bounded output. And then what you have learned in there is that that's equivalent to saying that the one norm of the impulse response has to be finite. Okay. Anyway, this is something that typically we teach in the beginning when we say what is bounded with Bible stability, what does it mean for linear system. When we usually write to that, but what we do is we usually prove it explicitly by saying like this is upper bound, this is lower bound, and you get this. But the Young's inequality is a one shot, right? It's just there already. Okay. But now you can use Young's inequality also the other way around. You can also say, I can put the infinity again on the R, but now I'm swapping these two guys. So I can put the infinity norm on my impulse response, and I put the one norm on my input. That gives you other kind of system, other kind of stability notions, right? So in particular, if you do that, then you can see that whatever this norm we want to call, the one infinity mu norm, that one is smaller than infinity even for an integrator. So because the impulse response of an integrator is obviously still bounded. So meaning you can get different kind of stability notions, right? It's different from this one, from the Bible stability. Bible stability, as I said, means in the linear systems case that there are one norm is bounded, but there are one norm of the integrator is not bounded, obviously. So you get different things. Okay. Now, now Bible stability. Bible stability just means to choose infinity norm for both input and output. And then we get exactly what I already did there. Okay. That's it on signals and norms. That's the real criteria. So the first thing you will learn now is the small gain theorem, which I don't know if you have heard before or not. Have you heard of small gain theorem? Ah, okay, yeah. Okay, well, that's fine. Of course, then you learn that. Okay. Okay, what's the small gain theorem? The very distance idea here is just to say, I want to keep my gain small enough so that I cannot encircle -1. No? Meaning, obviously, I want that sort of my Nyquist curve stays strictly inside of the ball of radius 1 around 0. Right? That's sort of the idea. And yeah, you can do this obviously also just for nonlinear systems. Nobody prevents you from doing such a thing. Okay? So what does it mean, really? Well, typically, if the small gain theorem is formulated in a system like this, where you have the feedback interconnection of two systems S1 and S2, there's no negative feedback here, but it doesn't matter. Any negative sign you could put in here, stuff, right? So it's just a way of writing it. That's a more convenient way. And now our inputs are R1 and R2. Yeah? So you have two inputs now. Of course, if you want just one input, you might R2 equals 0, right? I mean, there's nothing lost here. Yeah. And our output signals in this case are E1 and E2, which sort of arrows, but they're not really arrows because we don't have any negative sign and stuff. But you call them E1 and E2. Okay, now let's assume that S1 and S2 are input-output stable with respect to whatever norms we have been choosing, some induced norm, and assume that the individual induced gains multiplied are smaller than 1. Then it turns out that the closed loop system from input R to output E is also input-output stable with respect to those norms, of course. So that's a small gain theorem. Just saying, I have two systems. Now, this system could have gain greater than 1, as long as this one has gains sufficiently smaller than 1, and I multiply them up so that the product is smaller than 1, things still remain stable. It kind of makes sense, right? One can make up for the other. Okay. Now, let's do a short proof of that, proof sketch. In case of the L2 gain, right? That's the one that you anyway learned already, I assume. So how do you prove it? Well, what we can do is now we can look at the L2 gain from R to E1, and look if it's bounded. And then of course we can do the same from R to E2, and if they're both bounded, then that's it. Okay, now how can we see this? Well, it's very simple. What is E1? Well, E1 is simply R1 plus everything that is fed back. Right? What is fed back? Well, it's the R2 obviously that comes in as input plus S1 of E1, which also comes in to make E2. Easy peasy. And now you can already see that this small gain theorem is pretty crude, because now just what we're doing is applying some little inequalities of norms, right? Now we're just saying, okay, triangle inequality of E1 gives me, okay, smaller equals than the norm of this thing, obviously. Okay, then what about the norm of this thing? Well, we just learned that, okay, I can use my gains, obviously, right? So if I multiply this guy, 2 norm with the gain of this one, it's definitely smaller than the norm of whatever comes out of it. And then, of course, I can do the same thing with the other thing here, right? Just applying it multiple times to these definitions of the induced norms. And then I end up with this inequality here. And of course, now I have my E1 here, and I have another E1 here, right? Which means I can solve for that one, essentially, and that gives me exactly this kind of thing. Right? Okay. Now, we know that the 2 norm of each of them is bounded. Yeah. Okay, and we also assume that now comes this product here, right, in the denominator. we assume that product is really strictly smaller than 1, meaning this denominator does not cause us any trouble. It will be always greater than 0. No? Hence, obviously, the E1 2 norm is also bounded, right? So everything is bounded in the denominator, everything is bounded in the denominator. Done with that one. I can do the same with the E2. And then, of course, if both of them are bounded in the 2 norm separately, then we can take the 2 norm of them together. It's anyway just a mark, a vector in a product kind of thing, right? I can split the norm in 2 components, so everything is actually fine. Oh, yeah, that's the proof of that one. That's true induced at least, and then you can do it for the other norms. It's actually the same way, because this inequality always works. Right? And it's more massive than strict triangle inequality. Oh, okay. Very good. Now, let's try to apply that to a system like that. Well, let's just discuss the case in general. Again, we have a nonlinearity that is bounded by this wedge, essentially, right? So meaning this thing here. And we saw that we said before that no matter what induced norm I'm using, it's smaller or equal to k, or it's equal to k actually, the gain is equal to k, right? But it depends on if we have a point where we reach the k or not, right? And then now if we apply the small gain theorem, then all it means is, okay, multiply k with the corresponding induced gain of my linear systems part, whatever it is. It has to be smaller than 1. And then that's it, right? If that is true, that's it. In case of p equals to 2, you discussed it, that becomes the H infinity norm. It's just the peak in your border diagram, right? So the peak in your border diagram multiplied by k, that's smaller than 1. And then you get exactly what we expect. So it's almost this, you can see now why Eisenman had this conjecture, right? Because if he had made this assumption that the nonlinearity is really bounded in this way, and he had this sort of small gain theorem assumption, then it would work. But it didn't work, of course. He was too greedy. Yeah? But he was not completely wrong. Okay. So I have been talking too much today. Finally, you're doing some examples with you. Huh? Yes. Yes? Mm-hmm. Yeah. Well, that depends on what you're looking at, right? Here we are looking at systems that are given, and we want to know if they're stable, right? So now you can say, usually the nonlinearity is something that either we decide or it's given to us. We have to decide on that. Let's say it's given to us, then you can say that, oh, maybe the system itself, there's a system, a process, but then you also have a controller that you're designing. Then you would need to decide a controller what gives you exactly that quantity, right? So that's one way of thinking of that. Yeah. Oh yeah, so that's a comment that you just mentioned. I always say greater equal to 0, obviously because, well, anyway, our k is assumed to be greater equal to 0. But you're not making k negative here. It cannot be negative. Okay, now you do this example. What you need to do in this example is obviously it's first need to find the transfer function. Then you need to compute the gain of the nonlinearity. And then, of course, you have to apply the small gain theorem too. No? So, try to verify whether or not that system is stable in the L2 induced norm. Yeah. And we can also connect here on this one. That this is the center thing function. Now we can yeah, that we also this one. Yeah, can yeah, this is stabilize condition by two and the equal to two and more. Yeah, that's the and only minutes of giving motion along the no uh this this always the norm of S Wi-Fi always break important one or equal one. So the yeah that's example of unstable would be that have here we must have them together or the one of the time is stable. Stable because it's yeah, so must have it. Right. I thought so super normal. This one also is stable. Yeah, yeah, yeah. One. You get one. And it gets to the consequence. But I don't think the perspective is possibly that we focus on the others. That is that one. I'm coming forward, checking yeah. But I think if you have right now, I'll say more before this thing is just like because the gas one, the episode is very obvious. That's why the last thing doesn't matter is minus. Yeah, and they don't affect that. No, yeah. Why should it be one? Okay, so because when tablet no, they all correct. Yeah, the function is something on this one. Yeah, it's okay. What I do is also well about what both yeah, it's very good thing. Look at something about what is it? what's the input? What is E? So that for E is the differential equation. That means that this R minus I, then E is your E, right? So and now you just want to know the transfer function from E to Y. So how to do that? Oh, you just put that in the form. Okay, so yeah, put it together. You have I mean, here Y, the output is state, right? That's why I don't need to write Y equals. We don't have times X times. Divide Y equals to 0, 1 times X times open. Yeah, it was. Yeah. So now I have this. One that is okay. That's not really cool. These are the systems. Yes, very hard to do because of fields. We have to check the things very soon. And it's just it's really right. Yeah, so that's the normal is the normal. About the YouTube slopes. This is the normal in the CRU. Yes, for the L2. Yeah, ah, yeah, and if you know the line is 3 I think it is still good. One for the town. Yeah, we look at the people. Oh, okay. Sure. Just started. Not first. And I think the most problem that you had was to find the transfer function. Okay. So let's discuss it. Yeah? Okay. We come to everything, don't worry. Okay, so here, this is obviously an E, right? So all you need to do is you need to compute the transfer function from E to Y, right? Okay, obviously, I know you can do that. So what's the transfer function you get if you do that? Yes. Huh? Did most of you get this? Yeah? Okay. Okay, so that's the transfer function. What is our psi? Yes. Alright. Okay. Now, in order to apply the small gain theorem, we need to compute the gain. Obviously. Okay. So now I said we should do it with respect to the L2 induced one, right? So it means we need to compute here the H infinity norm. Yeah, so what is it? Oops. Equal to 2. Why is that? Why is it 2? Yeah, in the border diagram. And how do you draw border diagrams? I'm repeating this now because I want to make sure. How do you draw a border diagram? The gain. And I don't know. I think most engineers learn it in DB, right? And then here we have for log. No, I didn't learn it in DB. Yeah, so in Sweden we teach it without DB. No? So it works equally well. Actually makes it a bit easier because then you don't have slopes of minus 20 dB and minus 40 dB and all of these things. You just get slopes of minus 1 and minus 2, which is equal to your degree here. So in that sense, it's actually nicer. And you can check that, or you can also make the choice. It must not be a drawing. You can choose between dB and just absolute values. Okay, but regardlessly of that, how do we draw this magnitude diagram? Yeah, all right. So we need to look at this small frequencies where we just plug in 0. And that's exactly a 2, whatever that is in dB. All right, so this is 2 more dB. And then, see, this is why it's means they don't use dB. They don't need to think about it. It's just 2 there. And then, where do we have our exactly 1? All right, omega equals to 1 because we have a 4 and minus 1. And then we go down here, right? And what is the slope here now? Minus 40 dB, right? Minus 40 dB. Right? Minus 20 is for one pole, and then we have here minus 40. And hence, obviously, based on that analysis, you have to know that this is a monotonically decreasing gain, or gain. And hence, it has to be assumed in the smallest frequency, which is 0, and it's exactly at 2. Easy peasy. That is something all engineers should be able to do in their head. Figure out these diagrams. Doesn't matter what one. Just the shape is important, right? So you should learn that. Okay, so this is 2. Now what about this guy? Yes. No. Yes. Huh? That is. Yes. Right? That's how it is. Okay. Good. So now let me just reveal my solutions to the writing here. Make it a bit. There's this. This is this. Right? So bounded by that. This is this. And small equals 4. And then the small gain theorem just says multiply them up. That's it. So 1/4 times 2, 1/2, 2 and 1. That's the small gain theorem, right? Has to be smaller than 1. No. That's it, right? That's only for the open loop. But now we're talking about closed loop. Right? Yeah? So now we're talking closed loop. What we know now, because the gain is more than 1 of these 2 combined, that's why this works. Yeah? So now you know that this nonlinear system is actually input-output stable. Yeah? That's not bad, you know? Okay. Okay. Yes? Yes. Yes. I mean, the theory, no. The small gain theorem works for anything. They could be dynamic. But in our discussion, we only talk about static nonlinearity. But the small gain theorem works also for dynamic ones. Yeah? But then you also need to compute it. And the problem is mainly that computing the gain for something that is either not linear or not static is already difficult. Right? So that's why we do usually these combinations. But in theory, no, there's no difference. Right? So people use this for all kinds of things. No? Yeah, small gain theorem is very often used in the literature, very often. No? It's a crude way. This is usually also, okay, this is actually my next slide anyways. Yeah? Yeah? Yeah. 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 Yes. But of course, you can use it also for design. I mean, there's no. That's also what you learned before. You learn how to check that a linear system is stable, and then, of course, you can try to design things that make it stable, like a PID controller, this kind of thing. Once you know how to do it, the other part is sort of follows from it. Now, what I was going to say is, This is very often used in the literature, no? But usually when somebody uses it in the literature, the next paper comes out and says like, oh, well, this is conservative, I did something better. Right? So this comes with the conservatism of it. So let's assume now I have changed my setup, yeah? And instead of having here this sinusoidal stuff, I just put my feedback as minus k, where k is some positive number. Then, what can we conclude about stability? So we can still do the same thing as before, right? We can still say that, yeah, like a physics. So we can still do the same analysis, right? And then if we do the small gain theorem, then the gain of our nonlinearity is just what? Equals to k, right? Obviously. So that means we get the same thing as before, right? Now we have our nonlinearity. Our nonlinearity is just k times y. Well, obviously, I mean, that gives me the gain is equal to k. Well, I'll get sloppy here. Should I choose to? But anyways, and then the small gain theorem just says, okay, multiply them up. So 2 times k is more than 1, meaning, of course, equivalently, k should be smaller than 1/2, right? But if we apply like this criterion, then we know that is stable for all k, right? Because if you look at this, this is now, as we said, the true Nyquist diagram of that system. No? And so if now I can see that I'm never intersecting even the negative real axis. So if I multiply by k, I will still not intersect the negative real axis as long as k is positive, right? So that's pretty bad. I mean, 1/2 versus infinity. That's pretty bad. And what is the time? Oh, yeah, okay, so that's last time. No, it is enough here, right? For linear systems, it's enough, right? So meaning that this thing that now works for nonlinear systems, it's actually pretty conservative if we just apply it to our linear systems theory. Right? So we can see there's a gap between those. Meaning obviously there's also a gap in the nonlinear case. Right? And in order to close this gap, we will have what's called the circle criterion. Yeah? So that's what we'll do next one. But yeah, okay, we can at least discuss this here and then we do it. Yeah? Okay. There's circle criterion, case number 1, so then other cases too, we will come to that. So this case number 1 is the most common case in a sense. Okay, what do we have here? We have again our feedback interconnection form. Yeah? And what we want to know now is whether our closed loop system is input-output stable from R to 1. Yeah? Now, what are the assumptions that we are making? And that's why I told you these pictures with these branches become important. Now, what we are assuming is that our nonlinearity fulfills this inequality. Now, what does this inequality mean? Well, divide by y here, right? And what does it mean? It means that k1y should be smaller than psi of y and should be smaller than k2 of y if, y is greater than 0. If y is smaller than 0, everything reverses, obviously, right? And if y is equal to 0, well, then this whole thing is anyway fulfilled. Right? And that's why it's written in this form here. But if you unpack it, unroll it, you will do this. Huh? Now, if you do that, and now we are assuming here that k1 is greater or equal to 0, and k2 is greater or equal to k1 and smaller than infinity, then we get exactly this picture here. But we have a positive slope k1 times y, and we have a positive slope k2 times y, and in between has to lie this psi of y. Yeah? Okay? And then of course for the negative y, it should be exactly the opposite. You have the negative slope, and then it should also lie between two. Yeah? This is exactly what this thing means. And another assumption we do in case 1, they will remove that, of course, in case 2 or 3, whatever, is that the T is not stable. Yeah? And now the criterion says, okay, under these assumptions, if the Nyquist curve of G of S, which is in this case, okay, this one here, the blue one, has neither encircle, yeah, so the red circle here should not lie in here, nor should this blue line intersect the circle. Then I have a closed loop input-output steady system. Yeah? Now, how do I get this circle here? The circle here is just defined by these 2 points, which are minus 1 divided by k1 and minus 1 divided by k2. Yeah? This is how you get this. Yeah? If you have 2 points of a circle, you know it's entire circle, right? Okay. Yeah, so this is how it is. So again, a very kind of frequency domain condition, right? You have the Nyquist diagram. You can draw this circle here very easily. And if you know that for a stable tree, you're not intersecting or encircling this circle, then you're done. Okay. And you will see actually that in this particular case, this will recover Nyquist criteria. It's chosen or it's given by a nonlinearity. Yeah? Yeah? It's not like we are choosing it. I mean, yes, we are choosing, when we are choosing it, it's more as tight as possible in order to make the circle as smooth as possible. Yeah? But otherwise, it depends on our nonlinearity. Yeah? Yeah? Okay? Okay. So, break, and then we will do the proof. Which is nice because it's just loop transformation. Yes, you check on the blue